In the last video, we talked about the indicator trick. Here, we are going to give the details. Suppose that we have our population where every element is either of type R, red or green or blue. From this, we draw a sample. The first is a blue. Then we have a green. So we have a sample of size 5. Let's write down the numbers 1, 2, 3, 4 and 5. Now I shall make a little table showing which color each of these things are. Here I write the sample numbers and here are the 3 categories. The first one is blue, so I will write a 1 here. The second one is green, so I write a 1 here. Then I have another green, so I have another 1 here. Here I have a blue and finally I have a red. And imagine that all the others are filled with zeros. We had counted the number xi of sampled individuals belonging to category I. You can get them easily by just adding. Total number of reds in your sample is 1, total number of green is 2 and total number of blue is also 2. So this is your x1, x2 and x3. So that is the indicator variable. Each of these things are either 0 or 1 and I can express my xi's as suitable sums of those indicators. Now we shall write it down mathematically. I shall define IKI, so that is the entries of these matrices, as 1 if the kth sample is in category I. So these are my k's and these are my i's. So this one is 1 because the second sample was green and I will define it to be 0 otherwise. So these are what are called indicator variables because they take only values 0 and 1. We also know that xi may be expressed as sum of these indicators. Just understand that whenever I am using the letter k, it goes from 1 to n, 5 in this case. The subscript I always goes from 1 to p, the number of categories. Now these are the 3 quantities that we were originally interested in. If I express xi's in terms of the indicators, these things can be simplified. But first we simplify these things a little bit. So we see the basic quantities are the expectations which occur here, here and also here. This quantity, expected value of square and expected value of product. So if we can compute these 3 quantities, then we can compute these. Now expected value of xi is basically this. So I can take the expectation inside to get. Similarly, I can expand this. Now when I expand this, I will get square of these plus the cross product terms. But since these are indicator variables taking values only 0 and 1, their squares are same as themselves. So this may be expanded to expected value of the sum, which is basically square, but being indicator they are same as the original thing, and this cross product term. Now I can let expectation go inside and we get this and this. Here remember that I am working with k not equal to L. Now, so the fundamental quantities of interest here are these because they occur here as well as here, and also this expectation of the cross products. Observe that since this is indicator and that is another indicator, they take only value zeros and ones. So that product also takes value only 0 and 1. So that's also an indicator. Here we are not working with that expected value of xi times x zeta. You can do that similarly. So take it as an exercise. In order to find the quantities, let's recall the definition of IKI. So expected value of IKI is simply probability that it is 1 because it is 1 times this probability plus 0 times the other probability. Since if I multiply anything by 0, it will not contribute anything. So I am writing only this part. So what is the probability that the kth sample comes from the ith category? And that is pretty straightforward, that it should be Ni by n. Because the kth sample could be anything of the n population entries, and the chance that it will come from category I is just Ni by n. And that holds for any k. Similarly, Iki times Ili, when will this be equal to 1? Where the kth sample as well as the lth sample comes from category I. So when you pick the kth sample, you can do that in n ways, because you have to pick it from the category I. When you are picking the lth sample, 1 is already gone because it is sampling without replacement. In the denominator, you do the same thing, except that now you do not have to worry about the category. You have doing for the entire population, so you have this. So now you can put this in the expression that I showed earlier and eventually get variance of xi and expected value of xi. Take it as an exercise to work out the expression for covariance of xi and xj.